Okay, up to you. Thanks, Lotte.
Okay, so thanks a lot for the invitation first to this very interesting workshop. And thanks for the introduction, Klaas. So I tried to frame the topics of my research around this workshop, but since I'm coming from an engineering background, everything is a bit more targeted towards an engineering perspective. And so as you've already mentioned, I joined the iTech Master Program, which was a unique opportunity to be taught by the visions of Professor Knippes and Menges. And then later I joined as a research associate at the ITKI with Professor Knippes, and now I'm at the blog research group. And so all these places are really important to me because they really influenced my work, my motivation, and my doctrine, basically. In case you don't know them very well, this is basically an overview of quite famous projects of ICD and ITKI. And I think what makes them particularly unique is the fruitful collaboration between ITKI and ICD, bringing together not only structural perspectives, but also the digital fabrication and the computational design. And their key fields is the coreless filament winding technique and segmented timber shells, so on and so forth. And the block research group is basically known for their funicular structures and, of course, Rhinovolt with their advanced digital tools. And my work that I will show you today is basically a combination of an outcome of a combination of the two doctrines of both institutes. Great places. And to put this a bit into context, my deep motivation is really to address the climate crisis we are facing at the moment. So I think Professor Gengnagel yesterday had a beautiful introduction on this, so I will keep it short. But as you know, we in industry have a direct impact into the global energy use, the energy-related emissions, but also the waste and resources. And as common knowledge, the world population will grow. So we really have to change the way we build and we design our structures. So from my point of view, we can do this either by building more lightweight and or by reducing the embodied carbon inside our structures. So meaning, for example, reducing the cement ratio in our concrete, making it a lower strength material. But I think we can challenge this because nowadays we really have the opportunities to approach this from an innovative perspective with our new technologies and also by learning from the master builders, which have created strength through geometry rather than through high strength material. And this obviously through local articulations in the structure and the overall global shape. Master builders like Nervi in the 60s picked this topic up, and always a key issue was basically how these shells can be formed in terms of formwork systems. So Nervi had this concept of the ferrocement, and nowadays there's a new phase of contemporary shell structures, which are enabled by our digital fabrication techniques. However, they entail a vast amount of waste. So I really question if this is the right approach. Bringing us to the bending active structures, because here only the material inherent behavior can be used to build a double curved shape. And of course, you know, the most famous example of the Multihalle Mannheim, which was erected with this principle. And nowadays, there's a multitude of examples, mostly in the Pavilion scale, that deal with the bending active structures, also addressing their simulation, which can be quite advanced. So talking also about materiality, because it seems to be also important for this workshop, not all materials are appropriate for bending active structures, and basically every material with the right ratio of low stiffness to high strength of 2.5 is suitable. So the popper you're planning to use fits perfectly in. And basically the idea of bending active is to use this ability of high deformation to program the shape of our structure. What the appropriate materials all have in common, most of them, is that they're composite materials, so either natural composite like wood or CFRP and GFRP, which are all embedded in a matrix, fibers embedded in a matrix. So very basic, what happens actually in bending, we have a tensioning on one side, which is a lengthening, and a compression on the other side. And this can be induced and actuated either externally by pushing up, down, or together, or internally through a pre-stress, which generates this contraction, or a hygroscopic contraction. And if we integrate both of them, we can, in the internal actuation, we can have this self-contained system where we shortcut the forces, thus reduce the support forces and free the edges. And taking this further, with combining it with membranes, this can have beautiful shapes and local articulations, and it's a really powerful way. However, it has challenges because it's not unlimitedly scalable, and at the same time, it really reacts not very strong from an engineering perspective to external loads, because of its low stiffness that is required for the formation. So basically what is demanded here is a reinforcement strategy, which can be either volumetric or through adding additional layers. And here comes in basically my belief that bending active tensor hybrids can be very suitable as a formwork system themselves. But I don't want to only limit it here to bending active structures, because there's a lot of other structure typologies that allow for lightweight structures or material efficient structures. And they're all characterized by the interdependency of the form and forces. So basically the ones that are not gray. And this I would like to also show you throughout the range of projects I've done so far, which all address the issue of generating a complex shape to enhance structural performance, but with different construction strategies, so not only limited to bending active. And I believe that this is possible if we approach it holistically, if we combine the computational design, the informed structural design, and the fabrication design, were from early design stages on. And also the fabrication technology can be either digital, but it can also be like a return to craftsmanship, as we will see later. So the first project I want to show you is Urbach Tower in the Remstal Gartenschau. It's a 14-meter high CLT surface active timber structure, and it gains its strength through its geometry. However, it's single curved, and but it has this appearance of double curvature through the interplay of the single curved elements. And why is it single curved? Because any continuous board can only be single curved, otherwise it would have to distort, and it cannot. So this is an example of internal actuation that is driven by this hygroscopic contraction of one layer. And basically the material computes the shape into a constant curvature, thus an arc, and without the need of formwork or surface milling. And this strategy was developed by a team of researchers from ICD and EMPA, not including myself. And I only came into play when it was about the realization of the demonstrator. But of course, we have to understand what materials we're using. And in order to keep it from further deforming, we had to lock the bend shapes with extra locking layers, which is also kind of a reinforcement strategy. And here you can see this torsional interplay of the cylinders that create those nice seams. And we also see the direct correlation between the primary fiber direction and the secondary fiber direction, which then are crucial for the structural design of the tower, because of course they're key to it, and this is basically my main contribution. But in order to analyze this structure, we really had to take into account in an integrative design process, this not only the structural design, but also the fabrication and the geometric design, because all has its reciprocal dependencies. From a global down to a detailing level. And we did this with manifold iterations within the Grasshopper environment and an interface to Sophistic. So in particular, we were interested in what the effect of the fiber directionality has on our structures, and also in a combination with the splice arrangement within the single panels, we had to loop between fabrication design and structural design. All of this is only possible or really cool because we use local material, digital fabrication, but at the same time also the high-tech knowledge of the craftsmanship from Blumer-Lehmann, which enabled also this high degree of prefabrication and also for very easy assembly on site. So in this manner, we result with this very lightweight, slender structure, which achieves its strength through geometry without the necessity of molds. Here you see the inside with its clean seams, and here the outside with the sharp seams that are kind of the key design feature. So as the next project, which is also a collaboration of ICD and ITKE, I want to show you the segmented timber shell. So it's an alternative strategy that doesn't have to do anything with bending, but it still creates strength through geometry. And it's relevant, I think, because also here the fiber directionality and the patterning of the segmentation plays an important role. So this is how it looks like with its 28-meter maximum span. And so the double curvature is created through the segmentation of these hexagonal cassettes, which are made of planar sealed LVL plates in this case. And they're fabricated robotically, of course, without the mold because they're planar and they can be assembled on site with limited formwork, almost none, which is very cool. But in order to achieve this, we again need this really integrative process. And in particular, for me, from the structural engineering perspective, it was interesting to see how the fiber orientation along the principal stresses correlates with the segmentation and, of course, the structural performance. Yes, so at the end, we have this nice lightweight structure, which is only enabled, of course, through this really novel digital timber construction approach. So then I want to briefly present the research Pavilion 2017 of the ITEC students, where I want to focus on the reinforcement strategy of the bending active frame that is used inside, which is not so known maybe, and also on the informed fiber layout. So this project was basically the work of these ITech master students, including me and also Kyriaki Goti, which will present tonight. So don't miss out her lecture. And the project and the design process was as diverse as the team, also including biomimetic investigation. But what I really want to emphasize here is the double curvature that is not only required for the strength, but also for the fabrication strategy, which is in this case the coreless filament winding, which means that fibers are spanned between two frames in a specific sequence to slowly build up an anticlastic shape. So no molds are required again, but we need frames to anchor the fibers, which need to take quite some amount of tension. And obviously one option would be to have this with quite some regular tedious non-elegant steel frame, or with an FRP actively bent frame, which was the key idea of our colleague Bruno Gengnagel. And the main aspect I want to highlight here is basically this reinforcement strategy and the fiber directionality, because the initial flat FRP plate that you see on the left is really wobbly, so that it can be bent into the shape. Of course, also we have to pay attention to the fiber layout so that it can nicely bend there. And then it must be volumetrically reinforced from the inside, and then also with carbon fiber, so that it really becomes like this strong performative frame, onto which then the fibers can be placed. And also for the placement of the fibers, it's crucial to have the double curvature, because this kind of dictates the possibilities of fiber directions. And of course, it has to integrate also the architectural demands. But this also doesn't go just alone. It has to go hand in hand with the structure design, overall shape, which is tailored in this integrative design process. And here you see the resulting outcome, which allowed for this 12-meter cantilevering pavilion. Of course, the use of FRP can be questioned, but this is not the focus of my presentation today. So maybe the most relevant project for this workshop today might be this one, which is our master thesis from the ITech program, which I carried out together with my awesome colleague Giorgia Margheriti. It's called Tailoring Self-Formation, basically of double curved shapes. And it focuses on the fabrication and simulation of these. So there is an increasing demand in customized geometries of unique double curved shapes. However, their fabrication with molds usually entails a vast amount of waste. So our aim was to construct double curved lattice surfaces on the basis of this inherent material behavior without the necessity of molds. And how we did this is that onto a pre-stressed high-strain membrane, we applied carbon and glass fibers in an informed grid layout with the tailored fiber placement technique that originates from aerospace industry. So actually, it's a pretty crafty technique, but it's CNC controlled. And after the curing, we release the membrane, and then it actively bends into this double curved shape. And what is actually happening is that we have this internal actuation, which is driven by the length difference through the pre-stress of the membrane. So there's other examples out there of self-formation, but I want to point out that self-forming systems are basically only a subcategory of bending active tensor hybrids, just that they're pre-stressed and not post-stressed in a way. But for us, the main focus of this research was to reveal the rules that underlie the self-formation. Basically, how does the grid form from flat to double curved? And starting from a target surface, how can we derive the grid that will end up in this double curved surface, which we call form approximation? So these are the rules of self-formation with all the different parameters that impacted the self-formation, for example, the eccentricity and density, but also playing, for example, with the composite stiffness by releasing the pre-stress at various stages of curing throughout time. And all of this we achieved through a close loop between digital FE simulations and also physical prototyping, which helped us to validate and tweak our simulation. So then these insights were all integrated into a design to fabrication process, where we start from a target surface, we analyze its curvature, and then we adapt the grid manually, but based on the self-forming rules that we have discovered. And then we feed it sophistic through our Grasshopper sophistic interface, and we evaluate the outcome, and we have to iterate a couple of times until we reach the desired shape, which we then can feed the information to the fabrication. But the most critical insight, I think, here is how we achieve the double curvature, because I mentioned before that continuous plates cannot take on the double curvature, but a grid can. And as we also see in the multi-Halle Mannheim, of course. So starting with the basic principles of eccentricity, which kind of we take from the single curved concept, we place the fibers either on top or below. But then what really has to happen is this distortion. And in order to emphasize this distortion, we bias the angles of our grid so that when the membrane contracts, it will distort the grid into the right direction so that we have either contraction or extension. And this works well in our simulation for the synclastic and anticlastic, but also we validated it with physical prototyping. It's not limited only to the single pure syn and anticlastic shapes. This is just to really state that we can do these, but we can also expand it with variations or articulations of curvatures. So the outcome is this double curved grid that we can construct without the necessity of any molds, just purely through the self-forming rules in digital fabrication. However, what's missing is to make this something now really useful to construction industry, and how this could be a viable contribution might be by reinforcing it. And this brings me basically to my PhD topic, which looks into the bending active tensile structure as formwork for shaping non-standard concrete structures, where the key motivation is basically to have a lightweight, limited waste formwork, which allows for informed structural shapes to ultimately reduce the embodied carbon and so on. So I imagine that the bending active in the tensile system, it doesn't need to be self-forming necessarily, can be the formwork for a concrete shell or a vaulted floor, as well as also the reinforcement, and together they can work as in composite action. This idea is actually not new. Already the Romans used reed centering for their concrete vaulting. And then in the 60s, inventors in the US picked up on this idea. And nowadays, there's also various research looking into all these examples. So, but I will not give you an overview of my current research now completely. I will show you some insight on one interesting project. I think it's in South Africa, and the system is developed for a showcase unit of sustainable concrete houses to upgrade informal settlements in South Africa. And in particular here, I'm focusing with the team on the corrugated vaulted floor structure, which is basically building upon the knowledge of the BRG with their funicular floor systems. But for this context, it must be a bit simplified. So we have a compression-only, very thin vaulted corrugated shell, which we then fill up with non-structural concrete with a low cement ratio. And the profiling, this corrugation, is designed to take on asymmetric loading. Basically, it has the shape of the vertical projection that corresponds to the envelope of all possible thrust lines. And this concept is used to reduce the embodied carbon emissions because it creates this funicular floor solution, which doesn't need high strength concrete nor reinforcement. And at the same time, this project also aims to reduce the impact by utilizing local materials. So in South Africa, alien plants, they are like invading and they have to be cut down because they're competing with the flora and the water. So, but they don't have a standard timber quality, so they can be they must be used in a different way. So one strategy is to use the timber for the formwork system, and to use the biomass as an alternative bio-based aggregate in this low-strength concrete. And at the same time, we also want to promote local labor and traditional fabrication techniques, which brought me the idea of using weaving, which is also used there in their very traditional ways of building houses. And it can be used as a shuttering for our corrugated vaulted floor system, which is made of these branches from the alien plants. And it gives this highly aesthetic surface finish. So the formwork would consist of a network of actively bent splines, on top of which then the shuttering is placed. And overall, it's a system of single curved developable elements, not to complexify fabrication too much. And however, the fabrication is very low tech, but of course the computational approach must be high tech because we have to achieve the funicular form of the floor, and we have to find accordingly the bending active spline network. And ultimately, this system would overcome the intensive waste that, for example, we see in this that takes place through CNC milling. But however, this is a very nice visual reference for the soffit of our system. But the work, my PhD is not limited to this kind of low-tech context, but also it can be for these more exciting shell geometries, for example, in the work of Mariana Popescu with her knit candela, which utilizes digital fabrication to create a formwork system. And of course, it's also like an originally crafty technique, which is now put on the next level of digital fabrication. But what's here the main niche I'm trying to address is that for these systems so far, we need to have the support structure for the anchoring. And if we would combine this with bending active structures, let's see what happens. But of course, because all this is complex, the data structures, the form finding, the Compass framework developed by BRG comes in really handy. And I'm really glad to be able to learn from them. Yes, so overall, I hope I could give you some inspiration and made you clear how the strength can be generated through geometry, but how this also gives us like a great opportunity to explore and design new types of structures with new types of digital or crafty fabrication in a more suitable way. Thank you very much for your attention.
Great, thank you so much, Lotte. I'll immediately pass on the word to Stijn.
Okay, thank you. Thank you, Lotte, as well. Indeed, it's not a coincidence probably that we present on the same day, because there's a lot of similarities between our research. Thank you also, Klaas, for the invitation. Just one small correction. I have actually finished my PhD, but I liked what you said about being the future, so I hope that still is true for me as well. What I will present today is also based on my PhD research on some concrete projects. But I first want to say something about the group I'm in. So that's VUB Architecture Engineering at University in Brussels. And we actually do quite a lot of different things. We're quite a small group, but still we try to combine different topics. I just show a couple of inspirational images here. So we are architectural engineers. So we always try to make a combination between these two. So the architectural work, but really using also engineering to make better architecture. And that can be in different ways. For example, we have a lot of research on circular construction, circular architecture, so also in the really building industry. As you can see here is a project that we did actually on campus with reversible connections and so on. But the research that I will present today is really more in structural design. And we do a lot of things there. So we have a tradition in deployable scissor structures. We even have a spin-off now with our group who really makes them for the event industry. We have tensile structures, so using textile and tensioning textile to really make efficient structures. We even have one colleague who is in Canada making ice structures. And also on the material level, we try to work on new materials, innovations, digital fabrication for these materials. So, for example, working also with biocomposites, with mycelium, as we think also have heard earlier this week in the presentation of Mette. And so what I present is a work that let's say combines a couple of topics that we have in our group. And as Klaas already mentioned, so the work that I did together with my supervisors, Professor Larzelat and Niels de Temmerman. And we always try to do research that is also, let's say, societal, let's say, relevant for societal problems. I also liked the quote yesterday. I think it was by Alexandre Dubor shared a quote by Cedric Price. So technology is the answer, but what was the question? So we always try to start from a real question. And it's a bit the same as what Lotte already said. So we see in the construction sector, we use a lot of materials. We also make a lot of waste. When we see these pictures, I mean, the human scale is actually disappearing in this. The structure that we make are smaller. So we really focus more, or at least in my research, on small scale structures, event structures. But even there, we see a lot of structures that are temporary, but also produce a lot of waste. So people really see them as something that can easily be discarded because they are temporary. And that doesn't have to be like that. But we see in the current, let's say, sector, if you look at, for example, the event sector or the sector of temporary structures, we actually see that on one hand, we have these very low quality structures that are maybe a bit too temporary even, with materials that actually last longer than the structure itself, but are not really reused. But we also see these very nice structures, these really architectural qualitatively robust structures, but they are often not designed to be reused. So actually, this is not a problem of solving waste. We really need to redesign our structure and think about a way in which we can design out waste. So it's actually more like a design problem. So we always try to think about how we can do that in different ways. So I've already mentioned deployable structures, scissor structures. So that's a way of making a structure that can easily deploy open, but also can be folded back so that we can also transport it. We can take it from one side to another. We can store it in between different events, or also reuse it multiple times. So it can be a robust structure to actually reuse all the components. But it can also be a kit of parts structure. So that's also a topic that I will be talking about today. It's a structure that can be easily disassembled. We can reuse all the components in the same configuration, but also in other configurations. So we really start to think about systems. So here an example also about these deployable structures. So as I mentioned, some of my colleagues, also my supervisor, Niels Temmerman, they started a spin-off even, looking at how can we actually use this knowledge that we have about these complex mechanisms and then go to an industry, an event sector industry, which is quite traditional, and see, and there's actually a lot of interest in this, how we can actually use these structures now for something that is actually useful or that will actually be used as well. But we see we have quite a lot of different ideas here, different expertises in these transformable structures, like we call it. But we expect a lot from our structures. They need to be able to be disassembled, reassembled, maybe even reconfigured for different angles. We have a lot of components coming together. Maybe we want even a deployment, so that's even more complex. And this, let's say, mathematical complexity even in the geometry is translated then to a technical complexity in the connections. It's often the connection, so you see it's very simple bars, but the connection becomes, although these are very nice designs of connections, becomes something that you really need to solve. You don't have a lot of tolerances and so on. So that was the motivation also for my research, is to look into active bending, also as a way to make more, not simple structures, but solve some of these technical complexities. So really think about material and the way material behavior can be used to make efficient structures. So I don't have to introduce active bending or bending active structures anymore, because Lotte also showed some very nice examples of that. But that was what really interested us, is this simple way of creating complex shapes from actually a very simple component that can be just a flat plate, for example. And then we make these very nice structures. This is also not new. This has existed probably as long as mankind. People have always used this flexibility of the material that they could find to make these structures really on a very intuitive way. So that's one of the benefits. But now we see these very nice structures coming up, also stimulated by evolutions in digital modeling. Now we can understand what happens. So we can also make an integration between what we know happens, so material behavior, the geometric implication that this has of combining different materials that are elastically bent in one structural configuration, and then these shapes that of course also need to be structurally viable, and that gives rise to, let's say, a whole new range of, I'm not going to say structural type, but new systems, new geometries, and so on. And so that's what we wanted to apply also to what we already knew about transformable or reusable structures that then also can be rapidly assembled. So what I want to talk about today is, of course, showing some examples, but also talk about this idea of complexity, high-tech versus low-tech simplicity. That doesn't mean that the structure itself is simple, but we can make it in a quite a maybe low-tech way. I think Lotte also mentioned something in that regard. So the question is actually, where do we have complexity? So first of all, what we often call uniformity of complexity. Okay, how can we spread the complexity? Sometimes we see very simple bars, but then they're connected with these very big connection pieces, joints, that then need to solve everything. They need to solve rotations, they need to solve the connectivity itself, maybe reconfiguration, deployment. But can we not use this element as well? But also uniformity generating complexity. So where do we want complexity? We want something that solve complex problems, of course, but maybe we can find a uniform system that can do that as well. So in that way, we don't have to make a lot of different components. Maybe we can do something with all the same components as well. So I will show you 2 different examples later that actually show some also different approaches to that, because actually the material behavior itself can be the driver for geometric complexity without actually making a system that is complex in itself. So you see some pictures. I also have one model. I hope you can see it on the screen. I always like to show at least one model. It's a bit different if you're not live. But so this is actually a system. It's based on a system that was developed by the Coda guys in Barcelona. A very simple system where you have these grids that can deploy, but the connections, they are not on the same line as you would expect. So you have here a curved line, and that makes them fold if you unfold this structure in actually a curved way. So actually you get quite a complex behavior. You get a complex shape. This is a hyper shape, which is not what you would expect if you see this structure. But the structure in itself, making this structure is a lot more simple than making, for example, a totally mechanical deployable scissor system that in the end gets them the same shape. So these things motivated me and my supervisor doing the research to go look for different systems. So we always use this word system instead of structure, because it's really about thinking in a systemic way, where we can combine this idea of bending active structures with the concepts of transformability, reusability, deployability, and so on. And we use different tools for that. And one thing that we always realized when we were working with bending active structures, although sometimes what happens is quite complex and you don't always immediately understand the material behavior that is behind it, it's quite intuitive to make, for example, models. So that's why I show a model as well. Physical models were always a start for our work, because it's quite simple to get a grip on what is happening, to get a grip on the system by doing it physically, by playing with elements and so on. And we use them to then inform actually our digital model. Once we understood what was happening, we could also input it in a digital model, because you can put everything, of course, in a computer machine, but you have to understand also what is happening before you can actually understand what you need to do there. So these digital models, of course, were a bit more complex, because we had to also analyze what was actually happening in the system, include this elastic deformation and so on. So we did that, for example, with Sophistic. But then we also always went to the large scale, small scale structure, of course, but full scale, to actually see whether it worked and also prove, let's say, validate our digital models. So just quickly, the approach, let's say, for the whole PhD that I did was always starting from these components, but also this component behavior. So it's not just a bar, it's a component that can also deform, so it can also take different shapes. So it's flexible. But then also working with modules, so a very modular approach, where these modules can then be combined in the system, but also recombined, not always, but in many cases. But you also have these discretized components, these modules that can then be easily stored for different applications and different structures or needs. I will illustrate this with 2 examples that both use these principles, but a bit in a different way. So that's interesting also to put them next to each other. So the first one is Undulatus, which is a structure that we built in Amsterdam for a competition. So the goal was really to make a temporary installation that could easily be assembled, but also disassembled and reused, which is based on curved line folding. And then the Reciprocal Dome is a structure we built in Copenhagen, which is a type of bridge shell structure using the principle of reciprocal structures. So first, the curved line folding system. So here you see let's say the final structure, but also what it looks like when it's taken apart. So it's a very compact system. It consists of 99 components, but no connections are needed, or no external connections are needed to assemble the system. So we started here from the idea of curved line folding. So you could say that that's a bit the bending active alternative to rigid origami. So we also fold system. It also comes from paper folding. But instead of folding along a straight line, we do it along a curved line. So that means bending forces are introduced in the system, but it also means that we create a kinetic system. So you can actually actuate the whole element by just actuating or deforming one piece, which is of course different from origami, where often you need to handle a lot of different facets of the plane separately. There are some examples of this already. So as I said, it started from paper folding, just like regular origami. It has been used in more static structures, like Sahadid architects. They did an installation at the Venice Biennale, where they plastically deformed elements, so that's not non-reversible, so it's also not a bending active structure, but still a very nice installation. But it's also been applied at ITKE, for example, in really kinetic systems like the Flectofold, which is a shading device. But we wanted to go back to that idea that I mentioned earlier of really having this module, this element. We chose a triangular element, but of course we experimented with different shapes there as well. This modular element, a deployable component, let's say, that could then be combined in different ways also for different structures. So we experimented conceptually a little bit. I also made a lot of physical models, as I mentioned before. That's very important for this type of research, to see what can we actually do with this component. Can we combine it in different ways? And then in the end, we chose for this system where actually the elements are interlocking in a way. So each time the leg of one component is connected to the flap of the other one. And like this, it becomes a bit like a puzzle. So it's like a 3D puzzle that you can make, especially also because the connections are really this interlocking system. So as you can see on the right, so you don't need to bolt things together, especially not glue things together, and so on. The challenge here, so in itself, it's quite a simple system. Experimenting with this with models was also not really a big deal, let's say. But of course, the model that we had to generate to get this system is a bit more complex. But of course, that's something the computer can do. So we made a fully integrated model for this digital model that starts from a base shape that we wanted and then goes to the let's say the fully populated one where we have all the components, but also immediately generates the components that we had to produce. We used the laser cutter for that, which could easily create the entire component, connections included. So here's a short video showing how that works. So we start from this base shape, which is then triangulated for these triangular components, which we could then adapt a little bit to this shape, of course. And we can immediately generate these components and also adapt them. So they are fully parametric, so we can adapt them, but also adapt them over the surface. So generate some more material where we need it, and some bigger openings where we need a little less material. So the structure was suspended for the exhibition. So we put some more material where also the connections would be. And you see immediately you get a layout of all the components that are generated that could then give already all the necessary feedback also to make then the connections like that. So, and with that, of course, with that script, once we had that, we could easily generate a lot of different geometries. Of course, depending on the geometry, also the components change. So this is not a uniform system, but this is also not a problem because we laser cut all the components, so it doesn't take longer, it doesn't take more material to make all different components compared to all the same components. Of course, we did have to then think about the assembly process. So we have 99 components that can easily be assembled, but they are all, or the majority of them, also a little bit different. So we really need to be clear about which component goes where. So we had a numbering system. But as you can see, the assembly itself is just clicking these components. It's polypropylene, so it's a very it's a flexible material that also is easily deformed to then fit these components into each other. Which went really quickly. So we had 2 days for the competition, but actually we could assemble the whole structure in 2 hours. So which of course was a big plus also for the jury. But of course, this is, let's say, it's a bit of a prototype. It's almost more like a physical model on full scale. So we're still seeing, but I won't show that today. We're exploring also with some master thesis students, how can we actually go from this to a let's say a bit more scale a bit more rigidity as well? And do we then lose this simplicity? So that's, of course, something we have to look out for, because that was one of the main benefits of this system, that it went so quickly and that we could do everything so easily, also the production itself. So then the second case is the Reciprocal Dome. So it's, let's say, call it the reciprocal grid shell. So it's like a grid shell, like like for example, the multi-hull in Mannheim that Lotte already showed, but of course a lot smaller. And also we use, instead of using all components that run over the whole structure, we use discretized components. So they're a lot shorter, but then connected in a reciprocal way. So reciprocal structures are, they're often called also mutually supporting beams, because always one beam is supported by the other, and so on and so forth. So actually, theoretically, and if you make a small model, you don't actually need connections, because they are interlocking and then fixing everything. Of course, in practice, you will. It's quite an old idea or concept. I think one of the first examples of this was found in drawings of Leonardo da Vinci, who did a reciprocal bridge design. And we wanted to see, we worked together for this with Olga Popovic-Larsen from KDK in Copenhagen, who is an expert in reciprocal systems. And we wanted to see then, okay, what happens if we apply this bending active principle, or this active bending principle on this? Can we maybe make more simple connections? Because we see one of the, let's say, the properties of reciprocal structures is that you always only connect two elements per joint. So that, of course, simplifies already the joint compared to, for example, a geodesic dome, where you have to connect maybe 5 components with one connection. But still, you have varying angles. They're overlapping at different angles in 3D. So it's not always easy to make a connection. Often you need to make inclination in different directions. And then, of course, all connections can be different. So then you have to also find a way to connect them in a very good way. So that's why we wanted to see what happens if we use bending active components, flexible components that can actually easily deform and then overlap, instead of making these very awkward angles at the connections. And as I said, we all also strived for, let's say, a sort of uniformity. So uniformity generating complexity. So we also wanted to see what can we do with actually one set of all the same components. Can we then still make some interesting, some nice structures that are seemingly complex, and of course they have this complex material behavior that we then really employ in the structure. And therefore we looked at regular polyhedra, so Platonic Archimedean solids, but also, for example, geodesic domes, who are quite uniform in the, let's say, the lengths of their components. And we started from that. So very different from the previous project in the Latus, where we really start from this base surface that we want to populate with these components. Here we thought, like, okay, we have this one component, this modular component, and which shapes can we then produce with that? So we also made a geometric parametric model for that. So starting from, here is a very simple example with a icosahedron shape, polyhedral shape, which we then populate with these flexible elements to create this geometric constellation. And we can also go within these polyhedra. If you know a bit about polyhedra, you know that they always have a dual. So you have the icosahedron, but then its dual geometry is a dodecahedron. And we can also move actually by rotating the elements, of course, in a digital model, and not yet in a physical model, go to from one to the other, actually using the same components, but connecting them in a different way. So we experimented with that, of course, still in using some small-scale models, seeing what we can actually do with this one kit of components. Of course, there's a lot of challenges, because we go from one small to a very big one with the same components. Of course, that's still a challenge. And that's why we also, Lotte also mentioned it, of course, structurally, this is maybe not the most interesting principle, active bending, but we do see a lot of ways. Lotte already mentioned using tensile elements, a textile, or you can use cables. There's actually a lot of ways to use, to reinforce these flexible components to make something that is in the end using the flexibility of the component, but still stiff by combining elements and so on. I'll not go in depth on that. But for these components that we use for our Reply Dome, we also want to see, okay, we cannot just use one flat element that will very much limit us. So we started to experiment with some modular components that we could bend, that could then be used for our structure, but then ended up with a very simple one, just 2 layers connected to each other with a different length, which then, by connecting them already pre-bent, pre-curved elastically, at least initially, making this component that is double layered, so has a higher structural height, but it's also already curved, so we didn't have to push and pull all the components that much when we were assembling them on site. Now, this residual force that we have in this structure, this is more structural intermezzo, of course also has an impact on the structural behavior of our components. So we have a component stiffness, we use a wooden lat, for example, has a certain stiffness, of course. We then connect it in a certain way, we bend it, but just by curving it, of course, we already created a whole different behavior. In this case, we curve 2 elements, we're connecting them to each other. They also cooperate, but also create a totally different geometry compared to the initial component. But you also have an effect of these residual forces that are in this element. So it's the same as when you tension a textile, for example, if you want to make a tensile surface structure, a membrane structure, because of the tensioning of this textile, this also generates a higher stiffness. And the same actually happens in these bending active structures. So by tensioning, we actually create also a higher stiffness. So you can easily see that here. So this is based also on a simulation that I did with using finite element software, Sophistic. So you see if you push these elements, you see a large deformation. But if you then include these residual forces, this deformation is a lot lower. So you do see a high stiffening effect. But this is not always the same. So we also analyze this configuration of 3 components in a reciprocal configuration. So really also, and that's quite complex in this software, we had to, of course, also curve these components elastically to include these residual forces that are in the components. So that's, let's say, computationally a bit of a challenge, although it's a very simple system. We did it by contracting some cables that then pull the system or the elements to each other. And in these results, we could see then, first of all, the difference between a single layered element and then a double layered one. So we see that it does geometrically already give us some extra stiffness. And also the effect of then including this residual stress. But in this case, if we load our structure like that, that's a negative effect. So it's not always positive, like in tensile structures, but because in this case we create some compression. But then if we load the structure in a different way, if we, instead of pushing on it, we start pulling the system, then we see a whole different scenario where actually the residual stresses have a bigger impact even in a positive way. So that's important to realize also. So there's a lot of debate about this. Of course, it's a wooden structure, so a lot of these stresses also disappear over time. But it's important to know that it's also not always a positive effect, because we have bending here, so we induce compression and tension forces in the system. And so that effect depends largely on that. But going back to the structure itself, so the main motivation for all this was, of course, to make a system that was also easy to produce, easy to fabricate, and easy to assemble. So you can imagine that in this case, it was no problem. We had all the same components. We could easily cut them all at the same time, and then fix the different layers to create this pre-bent component, fix the components in a geometric configuration. So we first made some modules and then start to assemble them. We didn't have a lot of tools. We weren't very well prepared, but actually we didn't need them. We need quite a lot of hands to push and pull to keep everything together, but we could have pulled everything quite simply together without any problems. So as I said, the components are pre-curved, pre-bent, so it's easy. It makes it easier on site. You don't have to, because it's 12 millimeter plywood, it's a bit difficult to bend that on site, but there is some torsion in the components to make sure that the alignment of the elements is quite nice in these connections. So we did have to really induce that on site. So the benefit is that these components still had some flexibility, and this way you can also, let's say, account for some tolerances, which is different. For example, if you make really a deployable scissor structure where one small deviation can make sure that it doesn't deploy at all. So here we also have a bit of delay, but in the end we did have a structure that is really stiff. Everything working together, the different layers, everything connected, closed spherical geometry. And we also constructed it a couple of times already. So one of the projects that I'm now involved in is also seeing, okay, can we actually do something with this system? Are people interested in using them, for example, for events? But also, can everyone construct this, or do you really need expertise? We were also contacted as the picture at the bottom middle by someone who said, oh, that's a nice structure, can I build this? So we just sent them some drawings of the different lengths of the components and how they were connected, and he actually assembled or fabricated and assembled the structure himself. So fairly easy. So you could say, and we also do some workshop with children, that it's actually child's play, and it's true in a way that actually understanding the geometry can be a bit complex, but it can also be a good way to start learning about geometry. So we use this in a workshop that we do every year with children at a science festival in Brussels, where we actually have them involved in structures and thinking about material and how material can actually generate shape by actually working with different geometries, and they can start to assemble. For one, it's a bit easier than for the other, but it's also a great way for them to learn. So it's also a topic that we regularly bring to the table if we talk to students, if we have master thesis students, but also in workshops. So I will now, to finish, just show a couple of pictures of things that we did together with the master thesis students and also students of the first bachelor. And let's say the idea of this master thesis student was to see, okay, what are other shapes that we can make? Are they still easy to fabricate, produce, and assemble? So let's say also thinking a bit about this complexity. Of course, we have some complexity of geometry and behavior, but is it still simple enough to assemble this also if you don't have a lot of knowledge? So experimented with a bit less uniform shapes than the sphere, but still using a very uniform kit of almost the same components, so which is of course nice, and which was always the outset of the project as well. And also in student workshops, so with Bachelor 1 students, so we didn't do complex parametric modeling and so on. So we really started from the system, but we want to do something hands-on with them, that they can really also see that you can do some prototyping, full-scale modeling and so on, that can also be really helpful to research work, but also in designing stuff. So really also thinking about this modularity. So as you can see here on the right, these modules that can easily be assembled, and the student then made also a manual comparing different ways of assembling the structure. So of course, if you just see the structure, it can be a bit complex. So are there different ways to do it? For example, first assembling everything on the ground and then fixing everything one by one, or a couple of connections to make it pop up, or do it really gradually and create this curvature throughout the whole process. And so we had a successful workshop there, creating actually this structure together with the students, so Bachelor 1 students, without helping them. We just gave them the manual and saw what happened. Of course, if we saw something going wrong really badly, we intervened, but it was actually not really necessary. And so this, let's say, proved in a very basic way already that it's actually not too difficult to do this at all. So these were the two projects. So I think for me, it was always interesting to see them also next to each other, because it's a different way of working, where you really start from this surface that you can adapt and then see which components do I need. But also these components, of course, were produced by laser cutting. So it doesn't really matter there, time-wise, resource-wise, whether it's all different components or all the same. Whereas for the Recycled Dome, we had this wood workshop. We could cut the wood, but we had to manually then also make the hole and so on. So if it was all different, of course, if you can do it at CNC, it's different. But in our case, we really wanted to focus, okay, with some basic tools, can we make something that is uniform so everyone can actually do it with a very low amount of technical appliances and so on. And so both of them actually were successful in their respective goals. So I want to just finish with a couple of, let's say, thoughts that I walked through also in the presentation. So first of all, it's not because we focus on let's say simplicity or let's say low-tech solutions technically, that there's no complexity in the project. So we realized that actually we're putting a lot of complexity also a bit more in the first phases of modeling and design. We really need to think about geometry, but also if you want to make a structure that is complex in shape, but still is uniform in dimensions of components, but also using this material behavior in the modeling process complicates it there, but can really result in something that is then technically very easy to produce. The connections are always very important, and that's this uniformity of complexity. So here we chose maybe sometimes to make a bit more of a complex component that's also deformed, but connections could therefore be really simple. Modularity, I've talked about that, so that's also a very important thing that we took on board in this project, really starting from this module that you can also go back to, so you can then reconfigure also these modules to then generate different geometries. And I want to come back also to these ideas. So technical solutions can and should also solve real problems. And so we try to think, and we were doing this the last couple of years, to also have this contact with different industries to see, okay, what is actually what you need? Because sometimes solutions that we think are maybe a bit too simplistic for them are actually already quite complex enough. So we try to also balance this. Okay. Thank you already for the invitation. And maybe there are some questions.
Thanks for your intervention, both Lotte and Stijn, of course. Thanks. It was really interesting. I think what is your conclusions also, Stijn, are quite nice to talk, of course, in the context of universities. And I think what we see in both of your projects or in both of your approaches is that you're indeed going out to real world problems, let's say. In the case of Lotte, we've seen, for example, the Pavilion in South Africa. For you, Stijn, you have the case with the kids that are learning by doing, and even for young students that are prototyping. And I think it's in both ways. I think this is quite a nice role if we can have, as an engineer and an architect, and even as academics, that we are still solving real problems, even though we think we're in a little niche working on a small thing, that it can become something bigger. And I especially think also on your master thesis project, Lotte, then, that you are now developing into other ways that is maybe going to help industry to build things. In there, it's very good, and it's almost a relief, of course, for everybody to see, and for the states, that they are investing money in people that are solving real world problems, because the academics stay far behind, far away from everybody, and we do love to talk about all these things. But you both take the challenge to solve real things. What would be my interest is maybe in both of you, these problems, in a way, you ask the questions yourselves, right? And what I would be interested in is how often do the questions come from outside, and that you have to solve something coming from outside. It's maybe a totally different question than going into the topic, but you already explained very well the project, but it's maybe a very general one. And then somebody from the public was asking for you, Lotte, also, if the form finding from the flat planar shape is done in sophistic, or is it only the final form? And I think it's a little bit the same for Stijn, I believe. Is it done on the final shape for the reciprocal dome, for example, because how do you treat the residual stresses in the timber? Because after a while, they're actually going away in the timber. So so maybe there's two questions that I would love to hear you both on these, actually. Maybe Lotte, you go first. Yeah.
Okay. Yeah, thanks for these interesting questions. I think it's really relevant to bring it always in the context, as you mentioned, with real world problems, but it's also a big challenge because obviously it's always kind of fun and easy to explore phenomena that you're interested in. And then at some point, you really have to question, why are we actually doing this? And I think for me, luckily, the ITKE and ICB, as well as the BRG, they're both very targeted on making sure that things stay connected to reality. But at the same time, I don't know if I got your question right. There's no one ever really coming from outside and saying, look, we have this problem. Can you give us the solution? Which I think would be also a great approach in terms of problem-solving strategies.
Well, I'm thinking of Bloomer-Lehmann that is doing that a little bit with the BRG group, I believe, that is asking some questions how to use their robot in the best way, actually, that they've bought. I believe it's for Bloomer-Lehmann or for another timber company, at least in Switzerland, that they ask, like, okay, can you help us to develop what we can do best with this machine, of course. And these are interesting thoughts that the industry is coming back to solve problems. It happens a lot in car manufacturing or something. That's, of course, the industries come back to academics to do new ways of fluid dynamics, all these things, to develop new tools. And it's true, usually, actually, as an architect or engineer, we're mostly creating our own questions at the moment, right? It's which would be interesting to see that they can get an advantage also to bring academics into the field. I mean, we have the question at the moment lately for a 3D printed bridge in France. It is a public command, and the competition involved a university, a structural engineer, an architect, and an industry partner at the same time. So the academics needs to support immediately a direct outcome that needs, of course, to be ready for the Olympics here in 2024. We lost the competition, but okay, still.
I think this is the timeline is also one interesting aspect you point out here, because often I think great things happen out of, let's say, frustration and emptiness in your thoughts, and then at some point you have an idea. And I think in industry they don't have the time to really think so much out of the box. Like first the researcher must be bored until he gets like the inspiration in a way, maybe. And and then obviously if you really work closely related to industry and also projects, then I think I always feel there's like this stress a bit of like how to approach problems also, like from a more pragmatic and a more researching perspective. But at the same time, I really find the projects that I did so far that were really directly related with industry collaborations really great. In particular, the Urbach Tower with Bloomer-Lehmann was really a unique opportunity, because I could also learn so much from the approach that they take and their way of thinking. So I think these industry collaborations are really fruitful and should be pushed further in many opportunities, I hope. And then maybe just to answer the pragmatic question about sophistic. So yes, we use sophistic to start from the flat sheet and self-form into the double curved. So it was purely sophistic based. Technically, it could also be a more lightweight simulation, which now I'm also more looking into. But at that time, it was the most practical solution for us. I don't know how you, Stijn, experience sophistic. I think also there I was interested in, because it's always a difference if you have beams or really like plate structures for the simulation, which what issues you're facing there, or yeah.
Yes, indeed. I'll maybe answer to that, because I also saw the question. It's also about complexity. So for plate structures, it's really indeed the complexity of the model is just immediately so high. So what I did for that is also work on different levels. So first start with just one component, so really elastically bending that so that works. It's already complex enough actually folding this element, because in sophistic there you really always have to start from this flat shape, of course. And then putting some components together. But actually when we did the whole structure, the full structure, we actually didn't consider the elastic behavior. So there we did actually just the final shape. So we used, let's say, smaller models to get a grip on about what was really happening to then inform, let's say, the bigger model. Because we also realized that, especially for the Reciprocal Dome structure, as Klaas mentioned, it's, we saw that after we took it down, it's quite quickly, these residual forces are gone and it just plastically deforms after a while. So that's why we want to know about this effect, because it can also be negative. So then we need to know that we really need to consider this. But we don't really rely too much in this case on the positive effect, because we know that that's only probably temporary.
And there was another question. Somebody was asking also how these structures can be used in high-rise. I think Lotte showed it a little bit. High-rise, I think it's not necessarily towers, but I think you showed already that certain of the techniques that you're researching can be used for making slabs and all this. So I think there's a direct answer to that. But maybe for Stijn, what would be your answer?
The structure that I showed now, it's mostly, it's really small scale. So we always focus a little bit more on that. So I don't think they could actually easily be translated to high-rise. But we do think also about, that's not really building high-rise, but also for, let's say, facades and so on. So then it becomes less of a structural component, but maybe more of an added layer. But we've had some ideas of people saying, maybe they saw the undulatus structure, for example. So it's an easy puzzle that then mentioned, okay, can you not use it for a formwork? That you make a formwork with this for a complex shape, but you can then take it out as well. So we haven't really done anything in that direction at all, but I think it might be interesting to also look into things like that. I don't think the undulatus will be a good fit for that, because it's also flexible. So I don't know if pouring concrete on that is really a good idea, but yeah, still, it could be interesting to look into that.
Yeah, no, I think so.
I think, just to point out, sorry to interrupt, or was it still about the high-rise, or were you moving on to the next topic, Klaas?
No, go ahead, please do.
Okay. Yeah, I just wanted to point out that basically there is research by the Block Research Group that is even like more relevant addressing high-rise buildings, because there's all this research into the vaulted floor systems, and because usually they're so when we can save up to 70% of weight with really optimized vaulted floors, then of course this has a huge impact on high-rise buildings, because then of course the entire rest of the structures requires much less material. So there's research there, and then also at the same time I know that ITKE and ICD, I think they're also addressing more now the questions of high-rise, or at least more like middle-rise buildings with timber construction within the excellence cluster. Of course, not with the shells segmentation approach, but of course with their mindset that they have with the digital fabrication and design. So I think that will be an interesting outcome, and I'm curious to see what it will be in order to answer these high-rise questions.
I think there's another question from Anand Shah about the rods, if they were coupled with fabric for form finding. I guess that's relatively clear. Yeah, they were glued on top of the fabric indeed to make the shape then move into the right form. I have maybe one last question, and then we can send you back home. I wanted to say, but actually you're already somewhere home, I guess. So both of you have several examples where it's more a question related for the students actually how you do the design process. So either you have a bottom-up or a top-down process. So I think when I remember the one from Stijn maybe now, is that the one that you presented in, I believe in Holland, is more a bottom-up, where you first start with an element and you see, okay, I can do something, and then you can make actually more shapes. You could use it for generally tons of different shapes, of course. So the other one, the reciprocal dome, is very obviously it comes from a dome idea, and how do you solve it with a reciprocal structure? But okay, it comes more, it's a discretization of the shape. And I just was wondering, is there any favorite way? Because I'm noticing, like with the manufacturing or fabricating for students, usually they tend to go from a general shape, and then like in the top-down process, and then discretize it into smaller problems. Whereas I think the advantage sometimes of the bottom-up is that you're checking more, like, okay, one module, and then generalizing to other solutions. What is your experience, and what would you suggest for other solutions?
Yeah, that's a good question. We often think about it. We also use this comparison often. I think this is a bit a special case in my case, because indeed it's true, like you said, so we started for the undulatus really from this curve line folding component, but then in the model we actually did start from this shape, or this X shape, and then created, let's say, a system of components that are all a bit different. Whereas the Reciprocal Dome is indeed, we start from this shape, but in making the shape we also thought about the fact that we could actually produce it with all the same components. So I don't think there is actually a preference. It depends a bit, I felt, about on also the way you will produce it. But in the undulatus, we knew we are going to laser cut it. So actually, it doesn't matter if all these components are different, because we have to input the file anyway. So if it's all the same, it doesn't take longer. It also doesn't cost more material. Whereas for the Reciprocal Dome, if we had to, so now we produce it in one day, we could all make all the components. If we had to do that with all different components, the way we did it now, that would cost us more than a week. So for us, that was really the choice that we had to make. I think geometry-wise or system-wise, we often start from a component and we have a feeling like, okay, we can do stuff with this, because then you also see that's really the system thinking. So I showed, I think, one slide where you have this triangular component, but actually you can also assemble it in different ways. So it becomes really a system and you can play with that. So I personally like that approach very much. But I think you need to consider all aspects of the production phase as well to really make a choice. So I wouldn't say, in my opinion, that one is necessarily better than the other.
Okay. Lotte, as a final touch to our meeting today.
Sorry?
Yeah, you have the last word for our meeting today.
Great. So I wish you good fun and luck for your workshop. It's really a great opportunity to present my work here and also to see the work of Stijn. I hope we stay in touch. And thanks a lot.
Definitely hope to see you soon in real life then again. But okay, take care. Thank you so much for your time. Thanks to the others. We have another speaker at 6 again. Some people, they are called. It's very interesting work, I believe. So I will see you back at 6 o'clock. See you later. Bye-bye.
Bye.
Bye.